Hey everyone, and welcome back to the AI Research Roundup. I'm your host Alex, and today we're diving into some fascinating AI research. We're kicking things off with a paper titled PRIMA.CPP, Speeding Up 70B Scale LLM Inference on Low-Resource Everyday Home Clusters. So, you know how running those huge 70 billion parameter language models usually needs some serious hardware? Well, this paper introduces a system, PRIMA.CPP, designed to run them on a cluster of everyday home devices. Think regular computers, maybe a laptop, using a mix of CPU and GPU, low RAM, even over Wi-Fi. It uses some clever tricks like managing model weights efficiently and parallel processing to make advanced AI like Llama 3 truly accessible at home. Okay, so one of the key techniques they use is called piped ring parallelism. And figure 1 here gives a nice visual of how that works. You can see they've got different devices, like a phone, a laptop, maybe a Mac Mini, arranged in a circle or a ring. The model itself, which has 36 layers in this example, gets broken down into smaller segments, those little numbered colored blocks. Each device processes a few segments, then passes the result along the ring to the next device. It goes around in multiple rounds until the final output, like the word hello here, is generated. It's basically a way to share the load across the cluster. So building on that piped ring idea, figure 6 here gives us some timelines to compare how well it actually works versus the more standard vanilla pipeline approach. You can see the different colored blocks show what each device is doing over time. Blue is computing, green is prefetching the next bit of the model, and that yellow block means it's loading from the slower disk. The key takeaway here is how piped ring keeps things moving more smoothly, even with mixed devices and slow disks, compared to the vanilla pipeline, which shows more delays, more yellow and white idle blocks in those lower timelines. Okay, so those timelines gave us a sense of the efficiency. Figure 7 here puts some hard numbers on it. It's comparing PRIMA.CPP, that's the line with the diamonds, against other systems like Llama.CPP, EXO, and Llama across different sizes of the Llama model. The key thing to notice is how the latency in that time to first token, or TTFT, shoot up for the other systems as the models get bigger, especially beyond 30 billion parameters. But PRIMA.CPP stays significantly faster, much lower on the graph. You can also see lines showing PRIMA.CPP without prefetching or without its special assignment algorithm HALDA, and they perform worse, showing how important those techniques are. So we saw PRIMA.CPP is faster, but speed isn't the whole story, especially when you're running these huge models on regular devices. Figure 9 here looks at memory usage, how much RAM and VRAM each system uses on each device in the cluster. If you look at the plots for EXO and Llama, especially as the models get bigger, like Llama 370B, you see those bars getting really tall, hitting or even exceeding the memory limits shown by the dotted lines. But then look at PRIMA.CPP at the bottom. The memory usage is much lower and more balanced across the devices, staying well within bounds. This better memory management is likely a big reason why it avoids slowdowns and maintains that speed advantage we saw earlier. So yeah, that efficient memory usage really ties it all together, doesn't it? PRIMA.CPP shows it's possible to run these huge 70 billion parameter models much faster and using less memory on just a few regular computers networked together at home. This is pretty exciting because it could make powerful AI much more accessible, to folks without giant data centers. It really pushes the boundary of what's possible on everyday hardware. Well, that's all for this episode. Thanks for tuning in to the AI Research Roundup. I am Alex.